Welcome, ladies and gentlemen, to our lecture on units, measurement, and reporting results. Measurements are obviously very important to science in general, and they're especially so to physics. So let's talk about those for a second. There are basically two classes of measurements that I want you to know. One is a direct measurement. This is a pretty limited group. There aren't that many things that we can measure directly, but when we talk about a direct measurement, we're talking about something that you can say, for example, like length, where we can hold up a ruler to it and measure it. So for this class, when we're looking at direct measurements, we're usually talking about length, mass, and time. And when we talk about indirect measurements, we're usually talking about something where we measure something directly and then we do a calculation. For example, when we measure speed, what we measure directly is a distance that's covered and a time to travel that distance, and then we do a quick calculation and we come up with speed. There are many different things we can have indirect measurements for, and this class is going to have a large number of them. But for direct measurements, we usually have these three, at least for the first 2/3 of this class or so. So with that, let's move on to units. What are units? Why are they important? So units are standards that allow us to add meaning to quantities. So think about the physical world. If we have the length of something, let's think about the length of your index finger. Okay? If we have the length of something and we want to measure it, if I said it was 8, that wouldn't really mean anything, right? It's just a number. It doesn't really have anything to do with the physical world. If I said it was 8 centimeters, then it is a particular length. It has a magnitude, the number, and it has a reference to something, the unit. And now that I have a unit, this is a quantity that means something in the physical world. It's a particular length, and in this case, it's about the length of my index finger. So for the majority of this class, we're going to be concerned with 3 fundamental units. Those units are time, length, and mass. And you notice these 3 fundamental units match up with those quantities that I told you we can take direct measurements of. Okay? So the units for these 3 quantities are going to be the second. For length, it's going to be the meter. And for mass, it's going to be the kilogram. And the variable that we're most often going to use for these things, we're going to use t for time generally. We're usually going to have length as either x or sometimes an L. And mass, we're usually going to write an M for mass. So those are the 3 fundamental units that we're going to be concerned with, but we also have a number of quantities that can be expressed as combinations of these units. So for example, speed, you might have seen in the speedometer in your car expressed in miles per hour. So we have miles per hour for speed. In this class, we're going to express that as meters per second, because in this class, we're going to use the international system, or metric units. The international system is a system of units where going up or down in steps is by a power of 10. So if you think about our imperial system that we have in the United States, you might think of something in feet, and then there's 12 inches in a foot. But if you go up a step to, say, a yard, then there's only 3 feet in a yard. Or if we go up even a bigger step to a mile, there's 5,280 feet in a mile. And these numbers, these steps, are terrible steps. They're nonsense steps. It's odd to have such weird numbers make up these things. When we use the metric system, the reason we use it is because, for example, say we have 1 meter. If we want to go down a step, we would have 100 centimeters in that meter. Okay? Or if we wanted to go up a step, we would have 1 kilometer is equal to 1,000 meters. And we have these nice powers of 10, these nice round powers of 10 that we go up and down by. This makes the system much easier to use in general. And all we have to do to use this system is remember these prefixes that go onto our units. So the prefixes basically give us a power of 10 that goes on the unit. So, for example, if I have 5 centimeters, that means I have 5 times 10 to the minus 2 meters. The centi, the prefix on this thing, means 10 to the minus 2. As another example, we could have a kilometer that equals 1 times 10 to the 3 meters. We could also have 1 millimeter, and that equals 1 times 10 to the minus 3 meters. So milli means 10 to the minus 3, and kilo means 10 to the 3. This makes the system really easy to deal with, and all you have to know are these prefixes. So you can find lists of these prefixes. As we come across them, you should learn them and remember what they mean. At least the ones that we use repeatedly, you'll start to remember what they mean just by seeing them over and over again. So going back to an example, if I have 0.005 meters, that's 5 millimeters, or 5 times 10 to the minus 3 meters. And those are all the same. And it's easy for us to go up and down in unit magnitude because it goes by powers of 10. We don't have to do any kind of unit conversions. We can just move decimal places, because a power of 10 just moves a decimal place, right? A minus 3 just means that we take a decimal place. So we have a 5, and then we have millimeters. Minus 3 means we go 1, 2, 3 spots to the left. And that's the number that we have, right, in meters. Whereas the 10 to the 3, a positive power, would tell us if we had 5 kilometers, we would be going 5 and then 1, 2, 3 spots to the right, because this is a 10 to the positive 3, or 5,000 meters. And that's all we have to do to go up and down in units of the same quantity. So when we have length, when we want to go from millimeters to meters to kilometers, all we have to do is do powers of 10 and move decimal places. So I want to take a second here to give a quick note about powers of 10. A power of 10 is called an order of magnitude. So 1 power of 10 equals 1 order of magnitude. And when things are changing by orders of magnitude, they're changing very quickly. So don't be fooled when things are written in scientific notation into thinking that things are much closer in size or much closer in magnitude than they actually are. So as an example, I want to write that the mass of the sun is 2 times 10 to the 30 kilograms. okay? And the mass of the Earth is 6 times 10 to the 24 kilograms. Now, those seem like both absurdly large numbers. They're not that far apart. There's only a little difference of 6 in the power there. So they don't seem that different. But a difference of 6 in a power of 10 is a difference of 1,000,000. So a 1 with 6 zeros. A difference of 1,000,000. So what this actually tells us, 2 times 10 to the 30 versus 6 times 10 to the 24, it tells us that the mass of the sun is greater than 300,000 times the mass of the Earth. Or to put this in another way, the mass of the Earth is less than 0.0003% the mass of the sun. So these two numbers don't look all that far apart because they're written in this power of 10 notation, but the reality is we're dealing with one thing that's a tiny fraction as large as the other thing. So I want to point out that when we're dealing with orders of magnitude, when we're dealing with things changing in powers of 10, be aware that the change is very quick. Things grow far apart very quickly when we have order of magnitude changes. As one very quick example, one last one, the difference in size between the length of your hand and your height is about 1 order of magnitude. So keep in mind that even just 1 order of magnitude can mean that two things are very different in size. So with that, let's move on to math with units. So we said that when we describe physical quantities in the world, it requires both a number and a unit to become a physical quantity. It requires a magnitude and a reference. In a physics class, when we do math, we're representing the physical world. That's the whole reason that we do math. So our equations are going to have to consider both numbers and units, magnitudes and references, so that they're always referring to quantities in the physical world. So let's think about, for a second, the conceptual idea of addition. So 3 plus 5 equals 8. Pretty straightforward, right? But what if I wrote 3 centimeters plus 5 seconds? What would this even mean? These quantities can't be combined in this way, right? I can't add 3 seconds to, or 5 seconds to 3 centimeters. It doesn't make any sense, right? So that gives us our first rule of math with units. When we add or subtract, we must have terms with the same units. Okay? So addition and subtraction, of course, are the same fundamental thing. Subtraction is just the addition of negative numbers. So anytime we do addition, we have to have things with the same units, terms with the same units. So if I have 3 centimeters here plus 5 centimeters, now conceptually that makes sense, right? Now I would have 8 centimeters. These things can be combined in this way. And that makes conceptual sense to us. So that's our first rule for math with units. We must have terms with the same units when we add or subtract. Now let's consider instead multiplying and dividing. We know that if we wanted to measure the average speed over some distance that you covered, we would have some distance and we would measure that distance, right? Say it's 6 meters. And then we would time how long it took you to cover that distance. Let's say it took you 2 seconds. And then to get your speed over that distance, we would say that you traveled 6 meters and it took you 2 seconds. And we would divide 6 meters by 2 seconds and get 3 meters per second. And this gives us our second rule of units in math. And our second rule of units in math is that when we multiply and divide, we can combine different units, just like we did here. So now we have a new unit, meters per second. Per means divided by. And this new unit is a unit of speed. And this is okay when we multiply and divide. When we add and subtract, we need terms with the same kind of unit. When we multiply and divide, that's how we come up with new hybrid units like this unit of speed. So now let's think back to what I talked about in the intro lecture, where I said that an equal sign tells us that two quantities are the same. So when we're dealing with quantities in the physical world, we said that a quantity requires both a number and a unit to describe a physical quantity. If our equations describe physical quantities, then both the number and the unit must be the same for the quantity to be the same on either side of the equal sign. And this brings us to our third rule for units in math. Our third rule of units in math is that the units must match on either side of the equal sign. This means that on any equal sign, for it to be true, the units must match on either side. So this tells us in an equation like this that the unit of force is kilograms times an acceleration, which is meters per second squared. So the unit of force is kilogram meters per second squared. And because kilogram meter per second squared is a mouthful, we rename that and we call it a Newton. But this equation gives us a definition for the Newton. The Newton is a kilogram meter per second squared. So using our rules of math with units, we can then employ a few tricks that help us solve problems and help us with the math that we want to do. So our first trick for units in math, following these, are rules for units in math. Our first trick is that we know in general, if we have an equation, let's go back to our really simple addition here. 3 plus 5 equals 8. This is an equation, right? We know that if we multiply one side of the equation by 1, it doesn't change anything, right? This has changed nothing. 1 times the quantity 3 plus 5 is still just 8. So the way that we use this to our advantage with units is that if I can think of some equivalencies, for example, 1 inch is equal to 2.54 centimeters. This equivalency I know is true, and if I manipulate this algebraically, if I multiply both sides by 1 over 2.54 centimeters, then what I end up with is 1 inch over 2.54 centimeters equals, and then on this side, the units cancel and the 2.54s cancel, and I just have 1 with no units. So what does that mean? That means anytime I have some equation, I could always multiply it by the quantity 1 inch over 2.54 centimeters, and it wouldn't change anything. So how do we use this? The way that we use this is for unit conversions. So imagine that somebody measured something for us, and they measured it at 3 inches. But we don't want it in inches because we don't use that anymore. We use international standard units. We're going to want it in centimeters in this case. So I know that 1 inch over 2.54 centimeters equals 1. And I know I can multiply anything by 1 without changing the value of the quantity. It's also true, if I have this equation written like this, that 2.54 centimeters over 1 inch must also be 1. Okay? It doesn't matter which way I write this fraction, it's still going to be 1 because 1 tells me that the numerator and the denominator are the same size. So it doesn't matter which way I write it, it's still going to be 1. So in this case, I can multiply something by 1 without changing the value. So I'm going to multiply it by something that's equivalent to 1. And that's this 2.54 centimeters over 1 inch. Okay? When I do that, these inches cancel, and what I end up with is 7.62 centimeters. And this is what we call a unit conversion. And this unit conversion operates on the principles that units use in math. So the fact that we can have this equivalency to 1 means that we can multiply it by anything, and we can use that and cancel the units because they act just like variables in mathematics to come out with a new unit. So let's consider one more example. Think about weight. When I think of weight, the one thing I can always remember is that 5 kilograms is equal to 11 pounds. So then if I manipulate that equation algebraically, I have 5 kilograms over 11 pounds equals 11 pounds over 5 kilograms equals 1. Okay? So I have this relationship. And the reason I choose this one as an example is because I don't have to remember that there's 2.54 centimeters in 1 inch. I can remember anything as long as it's exactly equivalent. This one I find easy to remember because 5 and 11 are nice round numbers. I don't have to remember any decimal places or anything like that. It's just 5 kilograms equals 11 pounds. So I have these nice round numbers. I know that they're exactly equivalent. Anytime I can remember an exact equivalency like this, that's good enough for unit conversions. So then I can use this by saying, let's say somebody weighed 173 pounds. But again, we don't use pounds. We use SI units. So I want to change it to SI units, so I multiply it by one of these quantities. I want the one with pounds in the denominator because what I want to do is cancel out pounds in the units. So I have 5 kilograms over 11 pounds. That's equivalent to 1, so I'm not changing the value of this 173 pounds. The quantity is the same, and the pounds cancel out, and I end up with 78.64 kilograms. And we used any equivalency that we can remember to get us from pounds to kilograms. The second trick that we can use to make units work for us is that we can check our work. So imagine we solve a problem. For many problems, we'll have math that occurs in multiple stages. So we have this equals this, which we simplify and it equals this, which we manipulate again and it equals this, and then at the end we have some answer. So we said that the units must be the same on either side of an equal sign because the quantities are the same. So one thing I can do is when I finish some problem that I've solved, I can look at this and make sure that my answer has the correct units. So I know I'm going to have newtons because I was finding a force, and then in my answer I have kilogram meter per second squared, and this checks out. That is what a Newton is. So that answer works. But beyond that, if our answer didn't work, it isn't just that units work out in the end and that they'll be correct in your answer. They'll work at every step along the way. So I can look at this and see what units I have. And whatever my units work out to on this side, they must be the same on this side. So let's say that those match and they're good, but I know my answer's wrong. And then let's say that the units are still good here. Okay, these units are the same as the units above here. They still match. And then I come to here, and these units don't work anymore. The units on either side of the equation, now they don't match. So they worked here, they worked at this one, they worked at this one, and then they stopped working here. That tells me that I made the mistake going from this step to this step. So somewhere in here, I made a mathematical error, and I found it quickly and easily because my units stopped working from one step to the next. So this is the second way that we can use units to help us. One, we can make sure that our units are correct in our answer, right? And two, if our answer is not correct, if we did make a mistake, it's common to find the mistake just by checking the units at every step along the way and figuring out at which step our units stopped working. So with that, let's move on to uncertainty and significant figures. We know about units now, and so let's think about when we want to measure something. We want to measure something, and when we measure something, we're limited by the precision of our instrument. So imagine we have a ruler. Okay? We have this ruler. If we go to measure something on the ruler, we're limited by the marks on the ruler and our ability to discern whether something's between those marks, right? There's some level of precision that we can reach using this ruler, and then we're not sure about anything more precise than that. If we were to measure a similar thing using, say, a nice pair of calipers, maybe we could measure much better, okay? So let's say with the ruler we can measure down to 1 millimeter precision. And then with the calipers, we can do maybe 0.03 millimeters. Those two measurements have different levels of precision. We're sure about the length of something down to a different decimal place. So it's important when we report these values that we take this into consideration. We have to report it so that people understand how certain we are of our result and to what level we're certain of our result. So we take this uncertainty into consideration in two ways. The first is to have a plus or minus. So a plus or minus, maybe we would write that something is 5 plus or minus 1 millimeters. If we have precision of 1 millimeter. The plus or minus acknowledges that we don't know this value perfectly, but we have a degree of confidence that it falls in some range. So 5 plus or minus 1 means that something is between 4 and 6 millimeters. And we're sure that it falls in this range, but we can't be completely certain where in that range it falls. So that's one way that we acknowledge the limitations of our measurements. The other way is that we use significant figures. And when we report a number, we don't write it with arbitrary precision. We write it with what we call significant figures. And the significant figures let someone know where our uncertainty is. So consider again that we measured length and that we can measure length with the precision of 1 millimeter. So let's say we measure something to have a length of 8.7 centimeters. This would be the millimeter, so we have precision of 1 millimeter here. So we would write it at 8.7 because this is the smallest increment that we can measure. We wouldn't write it as, say, 8.73 centimeters if we only have something that can measure to within 1 millimeter, because this is smaller than a millimeter, and we can't actually measure this fraction of a millimeter. Okay? So we wouldn't write it like that. We wouldn't write it to some arbitrary precision. We also wouldn't write 8.70 centimeters because, again, we can't actually measure to this precision. So we wouldn't want to report that it's exactly 8.7 centimeters. We would report that it's 8.7 centimeters, and with significant figures, somebody would know that this is where our uncertainty lies. So when we do report things with significant figures, what we're saying is that we're sure of every digit up until the last one, and then there's some uncertainty starting with that last digit and going any smaller than that. Okay? So for example, let's say that something, we reported something as 7.53 meters. So we can measure down to the centimeter. If we report it this way, we're saying that we're sure of the 7.5. Okay? And there's some uncertainty at the 0.03. Now, the reason there's uncertainty at the 0.03, in this case we can measure down to the centimeter, is because we can't measure this digit. So we can't say what it is. So imagine the actual value, the true value in the physical world, it's off from that by 0.006 meters. Okay, it's off by 6 millimeters. If this is the case, and we can't even be sure whether this is added or subtracted because we really can't measure down to that point. So our actual value could be 7.524 on the low end, or it could be 7.536 if we're using this as what we could be off by, right? So if that's the case, it means that because we can't measure this millimeters place, we can't even be 100% certain of the centimeters place. We know that we're near the correct mark with the centimeters place, but we can't be 100% certain that it's exactly 3. You can see in this case it could be 2, or in this case even rounded up to 4. So there's some level of uncertainty with the 3, and that's because this place, this millimeters place, is completely uncertain. So when we write significant figures, that's what we're saying. We're saying we're sure of everything up until that last digit. The last digit should be close, but there's some uncertainty with it, and any digit after that, we have no idea. We're completely uncertain about what that digit might be. So when we deal with significant figures, we apply significant figures to scientific notation. And scientific notation simply means writing a number between 1 and 10. So let's say, 6.3 times 10 to some power. Okay, so let's say 10 to the 3. This is scientific notation, and significant figures are meant to apply to scientific notation. So when we think about them, we should think of applying them this way. So this number is 6,300. A power of 10 means that we take the decimal point from 6.3, we move it 3 times to the right, and that's the number, 6,300. So let's take an example of what significant figures might look like. So let's take some random number of meters, okay? If we were to write that in scientific notation, we would be saying this And what we're telling somebody, if we write it this way, is that we are sure down to the meter level. So we've measured this 6 million plus meters down with precision that's down to the 1 meter level. So we're not sure about anything smaller than a meter, which means that we're not 100% sure that this meter should be a 1. It could be a 0. It could be a 2. But we are sure down to the meter level. So we're totally sure of all of these. And this one we're close on, but we can't be 100% certain. And anything smaller than a meter, we don't know. That could be contrasted with something like this. And again, this one written in scientific notation would look like this. And again, we're talking about millions of meters. So now we're talking about just over 7 million meters. With this one, though, we're saying that our uncertainty lies here at the 100,000 meter mark, or the 100 kilometer level. So our uncertainty lies at the 100 kilometer level. So this one could be off by a little bit, and anything smaller than the 100 kilometers down here at the 10,000 meter level, we don't know. We truly we don't know this one. We haven't measured precisely enough to know something at this 10,000 meter level. So these two numbers, they're similar in size. They're both order of magnitude. They're 1 million order of magnitude. But this first one is reported with much higher precision than this second one, because our significant figures reach down to a much smaller level, a much more precise level than the significant figures of this one. So how do we do math with significant figures? Our rule is our answer must have the same uncertainty as our least precise input. So when we're dealing with addition, this means that we have to have significant figures that reach to the same place as our least precise input. So imagine we have 8.63 meters plus 4.717 meters. That is equal to 13.347 meters. But when we deal with significant figures, when we're dealing with addition, we can only go down to the same decimal place as our least precise measure. So this one goes down to the centimeter, this one goes down to the millimeter. So we can only go down to the centimeter in our answer, which means that this has to be 13.35 meters. That is an answer reported with correct significant figures for addition. And when we shorten our answer to significant figures, we always round. We don't truncate. We don't just chop off everything after what we care about. We round it. So since this is a 7, we bump up to a 5, and we have 13.35 meters. When we do multiplication, so now imagine we have 8.63 meters times 4.717 meters. That is equal to 40.70771 meters squared. When we multiply, we can only go to the same number of significant figures as our least precise input. So this one has 3 significant figures, which means that our answer, if it was written in scientific notation, would look like this. Okay. And we can only have 3 significant figures, so we can only have this much. So we round, and with 10 to the power of 1, we might not actually write it in scientific notation. So maybe we just write 40.7 meters squared. And this is our answer in significant figures, correctly reported with significant figures. So addition, we go down to the same decimal place as our least precise input. In multiplication or division, we go to the same number of significant figures as our least precise input. So since this is a 3 significant figure input, we have a 3 significant figure answer. Since this one in our addition goes down to the centimeters place, we go down to the centimeters place. If you were doing math, if you were doing a problem, say, and you had some stuff and you calculated an answer, and then the next step you had that answer times some stuff and you calculated a new answer, right? So this goes to here. You calculate a new answer, and then that goes in, and you have some stuff and you calculate a new answer. If you were doing that kind of calculation, you would want to carry the extra decimal places. So when I plug into the new calculation, I'd want to plug something like this in. I'd want to carry many more decimal places than my significant figures, and only round and reduce down to significant figures for my final answer to increase the precision of my calculation. However, in this class, we will not be calculating in steps. This right here is very bad practice. We will not be doing that. What we're going to do is we're going to solve all of our problems in variables, and we're only going to plug numbers in as the very last step, and then we'll find a numerical answer by plugging all the numbers in at once, so we won't have to worry about carrying extra digits, carrying things down like this. We're just going to put the numbers in one time and get an answer. When I start assigning homework problems, I will put out a video to show you guys the method for solving these homework problems, a method that works, that keeps you on a systematic and focused approach to solving a problem, and you will be required to solve the problems in that way. So there won't be any of these multi-step calculations. We're going to put our numbers in one time, but we'll cross that bridge when we get there. And this is the end of our lecture on units, measurement, and reporting results.